Today we will continue talking about reinforcement learning. Maybe first let's start with a bit of a recap from last week, right? So last week we introduced first like some exact methods like value iteration, policy iteration, Q iteration, very kind of like beautiful algorithms with guaranteed convergence via the Wellman contraction. But as we discussed, then they assume that you have a dynamics model, which we don't often in robotics. Then we move to like tabular RL, like Q-learning and SARSA, to start learning from experience towards like model-free models. And then we also discussed kind of how we can scale this up to robotics with continuous images and continuous action spaces with like starting from DQN and then towards DDPG and cross-entropy methods and so forth, right? And so essentially these were all the key innovations there in this last bit, that is like the deep RL part, were centered around different ways how to solve this like argmax in different ways. So everything we looked at last time was value-based, right? So the idea being that we try to learn the worth of every possible action, and then in a specific state, and then we kind of try to do the argmax to extract a policy. And we saw that it's a little bit difficult to scale this to to high-dimensional spaces, right? So the question we're going to ask today is like, what if we skip this, and instead of learning a value function and deriving a policy from it, why not just since we care about the policy itself, why not just like parameterize our policy and wiggle the neural networks of our network to produce behaviors that will achieve high reward directly, right? So trying to make our network produce actions that will lead to higher rewards in the future. So to wrap up our recap, here is the math also from last time to kind of like see where we are starting from. This is the standard RL objective that you've seen in the last couple of lectures. We are just trying to maximize the rewards as usual. We use a discount factor to trade off the rewards from today versus the ones from tomorrow. And then because the world is stochastic, we can't optimize with a single trajectory, but we optimize expected returns. All right. And finally, our trajectory distribution, to recap, is this one. So it's the three things multiplied together, where you start, what is your initial state distribution, then at each time step, the probability of your policy that assigns to your actions taken, and plus multiplied by your environment's transition probability. Okay, so let's say that we are starting to parameterize our policy, right, with theta, and we want to first understand how good it is, right? Because we cannot just like inspect our network weights to determine this. And this diagram here like captures this intuition, right? So from the same start date, like some trajectories are good, some are like kind of middle, and some are bad. And now, obviously, we want our policy to put more probability to the good ones, right? Now, the catch is here that we cannot calculate this expectation analytically because we don't know the true distribution over all robot movements in the real world. And so we kind of already prefaced this a little bit in the last lecture, but in practice, what we use is something we call Monte Carlo sampling. So we run our robot like n times using our current policy p theta, collect those trajectories and calculate the average reward. And the kind of like, we are making like an assumption here that that is maybe like not obvious, but we are making the assumption that all these data that we collect are coming from our current policy. So this is really what we mean by this is like an on-policy method. So we cannot use like past data to do this. So exactly, so we evaluate this expectation, which is a function of our policy, by rolling out our policy multiple times, observe the reward, and then average it to estimate how good our policy is. Okay, so we can evaluate this now with this Monte Carlo samples, but of course the main thing is we want to improve like our policy, right? How do we do this? So we need to estimate a gradient for this. So our goal is to maximize the expected sum of rewards, j theta, and the trajectories are being drawn from distribution pi theta tau. But there is this problem that we cannot like, it's not straightforward to get a gradient on j theta directly because there is this sampling process in between, right? So the relationship between both is kind of like implicit. So this means that we cannot simply differentiate through the robot moving in the real world, as they depend on the dynamics of the world, which we don't actually know. So what can we do about this? So we can do a little bit of math, where we can start by writing this expectation as an integral. So an integral of pi theta of tau times r of tau deta. Now, due to this integral being a linear operation, we can now bring the gradient inside the integral. And now, you might think like, well, this doesn't seem to help us that much yet, right? Doesn't seem so useful. But because we still have this high-dimensional integral that we really want to avoid to try to compute directly, and we still have this kind of unknown probability inside. But now there is kind of like a elegant trick of what we can do with this to rewrite this into a form that we can have it a bit more useful. So as I said, right, the integral here is not yet an expectation because you can't estimate it by sampling trajectories as you have a density gradient, not a density. So as I mentioned, there is this policy gradient theorem that allows us to rewrite this into a more useful form. And we will do like this kind of derivation a little bit here. So for this, we use this, what is called like the log derivative trick. So if you remember, the derivative of a log is 1 over, and then with the chain rule, we can get this very nice identity on the top right. Yes, and so here, if you look at this identity over here, we can see that the pi theta of tau times log theta of pi theta divided by theta tau, you can cancel this out to get grad theta of pi theta tau. And so here, essentially what we have done is just like we have multiplied and divided by pi theta tau. So essentially this means you're just multiplying by 1. And now you can substitute this grad theta of pi theta tau, the blue part, back into our original formula. And now this starts to become kind of like a bit more useful. Because now what we can do is we can write this as an expectation of grad log pi theta of tau times r of tau. And this is now something more useful because we can evaluate this expectation with samples, right? And we have here now kind of still this term inside that is not pi of A given S, right? So we don't still have like our kind of policy function, but we will get here in a second. Maybe looking at this, yeah, maybe you might look at this, the kind of like first part of the derivation, and you might be saying like, well, okay, like we have now this expectation over here, but we are still kind of sampling, right? And like I just said like a slide ago that we can't differentiate like get a gradient through the sampling process, right? Why this is helping us for now is that the difference is that now theta appears inside the expectation. So we can still differentiate through the sampling, that's correct, but we will be able to differentiate with respect to theta. If you remember also like the slides from last week on the smoothness of theta, despite having non-differentiable reward functions, for example, with the car driving through the mountain road. Exactly, so we can sample this term. Here it's kind of a bit more clear. And that term, the second term, it's still not differentiable, but through the sampling, right? Okay, so now we have this term over here, this log p theta of tau term. And maybe like here on the top, I've written again like the original formula for the trajectory distribution we just covered in the recap, right? So what can we do about this? So you might remember that the logarithm of a product is the sum of its logarithms. So if we apply it to the formula on both sides, we can get that we can write now this log pi of tau as the sum of log p of tau of S0 plus the summation from t equals 1 to capital T. So all the horizon of the log probabilities under the policy of plus the log, so under the policy plus the log of the transition probabilities. Now we can substitute this back to our policy gradient formula, right? And we can, when we have like the gradient of this, right? And so if we look at the first term, the log of S0, this doesn't depend on theta. So we can cancel this out. And if we look at the transition probability, this also doesn't depend on theta. So the gradient of it, we can also cancel out, right? Cool. So after this simplification, the only term left are the log pi theta at t, log pi theta at given st terms, which are the ones that we actually can evaluate. So, I mean, we also don't have the transition dynamics, right? So it's good that we can cancel it out. And so this essentially now gives us the vanilla policy gradient formulation. And we can now sample trajectories from our policy, compute a gradient for each of the log pi of actions, sum them, multiply with rewards, and then we can get a gradient to apply to improve our policy towards high rewards. And so this full algorithm is called reinforce. This is the acronym given by Williams in 1992. And this is kind of our very first policy gradient method. And sometimes it's also referred to as the vanilla policy gradient. It's quite simple, as you see. You start by initializing your policy. You evaluate an estimate of the gradients by collecting samples with the formula we just derived. Then you apply the gradients to your weights and repeat the process by collecting fresh data. And here, the n is the number of samples that you collect. So obviously, the higher n, the better, because you will get a more accurate estimation of your expectation. In a perfect world, you can have like infinite samples to have an exact equality and a perfect gradient, but of course that's not possible, especially with robotics. So let's build some intuition for what the gradient is actually doing. Probably the easiest way is to compare it to how the gradient for the behavior cloning formula looks like, something we covered a few weeks earlier. So the behavior cloning gradient is just the sum of the log probabilities of the actions taken. So you're maximizing the likelihood of whatever actions appeared in your data set collected by the expert, right? And so all actions get the same weight, no matter like if they were good or if they led to good or bad outcomes. The policy gradient here on the top is kind of the same thing. It's doing the same thing, but with the difference that now each trajectory is weighted by the total return. So intuitively, now good trajectories get pushed up and bad ones get pushed down. All right. Now let's talk about causality. So we have derived reinforced of our first kind of vanilla policy gradient, but now we can see where it starts to break down in the real world. Consider this example for the robot on the top, right? So imagine the task is to reach towards or grasp the cup, and but it overshoots and gets a negative reward in the end. So what does reinforce do? So it will penalize every single action in this trajectory, right? Including all the good ones in the beginning of the trajectory. And that's wrong, right? Because, the first part maybe was good behavior, but then, the second half was bad. And so essentially, what the gradient will be telling is to the robot, never move in that direction, because it led to a bad outcome. Right? So it will be really, really difficult to learn this behavior because you'll need a lot of samples. And so essentially this violates a little bit the causality, the principles of causality, in that in the physical world, an action taken at time step t can only affect rewards that happen either at the same time or in the future, but it cannot possibly be responsible for a reward that already happened in the past. So the first kind of fix that we can do to try to alleviate this issue is something called reward to go, where instead of multiplying the gradient of the action at time t by the sum of all rewards, we only multiply it by the rewards from t until the end of the episode. And so this way, we're not changing the expected value of our gradient, but we are reducing significantly also the variance and kind of trying to address this overshooting example. All right. Okay, so with this we have fixed causality, but there is another problem of this reinforced method, that is the high variance that I kind of mentioned right now. So imagine that now we have these two trajectories where one is the same, that overshoots, but we get a reward of 99, and the other one is a perfect trajectory and gets a reward of 101. And so effectively, this, the signal between these two trajectories now is 101 minus 99. That's 2, right? And that's the actual information content in what's the difference between these two behaviors in terms of rewards. But in reinforce, we will be computing the gradients scaled by 99 and 101. So your optimizer will be seeing this massive gradient updates where the true signal is essentially only 2% of all of this. So the rest is just noise, making your training very unstable. What we can do here, here you can see what I just mentioned. Okay, so we've identified a problem, right, in that just with this vanilla formulation, reinforced can't distinguish good from bad trajectories when the returns are large and similar. So the fix for this is quite simple. We can subtract a baseline B from the reward to go to center our rewards. That's the only change to the formula really happening here. Everything else stays the same. And now we are weighting each action log probability by the reward to go minus B instead of the raw reward to go. And what happens now in our case is that essentially now we are subtracting B equals 100. So that would be the average. And now the reward for our first trajectory would be -1, and the one for the second one would be +1. And now the gradient does exactly what we would like it to do, which is that it suppresses the overshooting behavior on the one hand and reinforces the good, the perfect reach behavior, right? So that's really like what ideally we want to be doing. Now you might be also asking like, well, this sounds a bit like cheating. Like, what are we doing here? Like introducing some random like constants into the formula. No, so we are not cheating here because in principle, like if you subtract a constant B, this doesn't change the expected value of the gradient at all. So it's kind of like a zero bias operation, but it helps enormously to reduce the high variance problem. Okay, so we've been writing this policy gradient with now this reward to go minus the baseline to reduce the variance. And we said that B could be like the mean reward, a constant that we subtract to reduce the variance. But if we look at this more carefully, like what are we actually computing, right? So it's kind of summing up all the rewards from time step t onwards, right? So everything that's happening after the current action. And we are taking the expectation over all the trajectories sampled from our policy. And this is actually, if you remember, like the definition of a Q function, right? Which is the expected sum of the future rewards given that you are in a state ST, and then you take the action AT and follow your policy afterwards. So essentially, this is very interesting. The reward to go is a Monte Carlo estimate of your Q function. So one noisy sample, essentially. So what we've been actually computing all the time is kind of like this noisy estimate of the Q function minus the baseline, right? So now that we have realized it, if we combine this with our baseline idea, we get what is called the advantage function, A of P of SA. So what you think about, like how does this, what is actually this doing? So if Q pi is the score that you expect if you take a specific action A, then V of pi is the score you expect on average from this state ST just by following your current policy. So what the advantage is trying to answer is how much better is it to take action A from ST. And if you plug this back into the policy gradient formula, you can see that now the positive advantage means that the actions was better than our average expectation, so it will increase its probability. A negative advantage means that it was worse than our average expectation, so we will decrease it. Okay, so here's our latest and most refined policy gradient formulation on the top. And it has the causality and the baselines, but it has still kind of like one practical issue that we mentioned in the first kind of like reinforced algorithm slide. right? That the trajectories are only valid if they are collected by the current policy, right? So this is like not super practical for us roboticists, right? Because we already know that collecting data with real robots is, very costly, and you have to robots break, motors break, and so forth. And so if, once you collect some data, and you do one gradient update, you have to throw away your data and collect again. This is super inefficient, right? It might be great for, in simulation or where it's easy to collect a lot of data, but ideally, we would like to be more sample efficient and maybe even do multiple gradient steps on the same data, right? All right, so the challenge is clear. We want to avoid throwing away our data. We want to make our policy gradient algorithm a little bit more off policy. How can we do this? For this, we can turn into importance sampling, which is a technique used to estimate expectations under one distribution when you only have access to samples from a different distribution. In our case, we want to compute our expectation over a target distribution, P of x, but we are stuck with samples, so this would be our new kind of policy. But in our case, we only have access to samples from Q of x, which is data collected with our old policy. So to do this, how we can write the expectation as an integral. We can use the same multiply by 1 trick from the previous derivation to add the term Q of x divided by Q of x inside the integral here on the right. And now by rearranging the terms there, you can put it into a more useful form, an expectation over samples from Q. I don't have a pointer, but this means that now we can simply weigh our function f of x by the ratio of p of x divided by q of x. So this means that now our robot can use our old samples, provided we weight them by the probability of that sample under the new policy divided by its probability under the old policy. One thing to note here is that this thing only works if Q has a non-zero support to remain unbiased. Because as you can see, if we divide it by, if Q0 is 0, then this will not be defined, this division. And so also intuitively, this importance sampling will work best if both distributions are not too far away, not like the case I plotted here where there's they're very, very different. Cool. How does this look like in practice in terms of math? So this is kind of our RL objective now with importance sampling. And how does this look like in practice? So we can start by inserting our trajectory distribution formula using the chain rule and substitute it for the old and new policy. Now we know that both policies will have the same initial state and the same transition probabilities, so we can cancel them out as they're operating in the same MDP. And so now we are left with essentially the ratio of products of the policy probabilities. And this is, as I said before, quite useful because we don't always have the dynamics of the world. And so this way we can now evaluate this importance weights. Now then, the next question is, how do we derive the gradient of this? Because in our gradient, we still seem to be sampling trajectories from the new policy and not the old one, right? So here, the gradient, we still are like sampling the new policy. So now we can use the derivation we did 2 slides ago for the expectation of the importance sampling and simply plug in those terms into the formula. And now the important trick here is that this now changes. Now we have an expectation over the old policy. So this is the data that we have, right? And so we expand now the importance weights with the product we derived in the previous slide. And this is still like a little bit troublesome because it is exponential in the horizon t. So this means that if, imagine that all our importance terms are less than 1. So if you multiply many, many numbers, like if t is very long and you have many small numbers and you multiply them, then their product will go exponentially fast to 0, meaning that your variance will grow also to go to infinity exponentially fast. Exactly. So this term is a little bit troublesome because it can be quite unstable with exploding gradients and so forth. In practice, we often consider expectations over time steps instead of over trajectories. So this is what we do, and we often, when we decompose this joint distribution of pi s and a, we get the action ratio and the state ratio. And while we can easily calculate our action ratio from our network, we cannot do this for the state ratio because we would need to know the global dynamics of the environment again, which we don't have, right? So in practice, this often is approximated by 1, which is kind of an approximation that algorithms now like TRPO and PPO do by forcing the updates to be small. But in essence, this gives us kind of our final form for that you see in the bottom. The important weights reduces to just a ratio of action probabilities of the new policy and the old policy. And again, it's just an approximation, and it will only work if they are like close enough. So here's how the full algorithm looks like in practice. In practice, it's not too different from like the reinforced algorithm we just saw a few slides ago. But now the key difference is that instead of collecting data and updating once, you now can collect once and perform multiple gradient updates. Of course, like you can't do this like indefinitely. You cannot like do multiple gradient updates before collecting again, because this would push your distributions too far, and then like the ratio would not work. So we've established that the importance sampling breaks down when the support set is 0, right? When the new policy pi theta prime assigns probability to action state pairs that the old policy, for example, never took. So what can we do about this? One kind of easy solution is to add an entropy bonus to the policy's gradient objective. So the idea is that we don't want our old policy to become too deterministic, so that it assigns 0 probability to regions of the action space. So we want really to encourage the policy to kind of spread out to reduce the chance of hitting the 0 support in the first place. And so that's essentially what we're doing here. So we can add like this kind of entropy term to the loss, and then we can have this temperature parameter that controls like how much weight we give to this entropy. The larger it is, the more like spread out it will be, and if you go closer to 0, it will be like kind of more greedy. There are kind of two different ways how you can implement this, depending on the action space of your robot. If it's discrete actions, then you can use the kind of standard Shannon entropy. And for continuous actions, you can use differential entropy for a Gaussian policy. And here, D is the dimensionality for your action space. So if it's like a 7 DOF, then it will be 7. Okay, we could talk more about this, but maybe let's move on for time. Okay, so we've talked a little bit about that the importance sampling only works when the old and new policies are close. But what happens if they're not, right? If we, as I said, if we perform multiple gradient updates and then it goes from the same batch, but then the policy changes too much before we collect new data. And here is like kind of like a specific kind of a failure mode example you can see where imagine that you have some action that was unlikely under the old policy, but it gets a high reward, so the new policy gives it like higher weight, or sorry, higher probability, and then the importance weight will essentially become very large, like let's say 20 in this case. So this will be really bad. Sorry. Because now your gradient estimate will explode essentially if like the importance weight is like very large. So one solution to this problem is to constrain the policy so it doesn't change too much during those multiple gradient steps that you're taking. One way how you can implement this is by adding a KL divergence constraint. So which measures how how close two probability distributions are. And essentially, like this will now penalize the new policy if it tries to assign, let's say, a probability of 0 to an action that the old policy took. Because the old policy data is kind of our ground truth data. That ensures that we have support for the new policy's actions. And this is essentially what the algorithm called Trust Region Policy Optimization, TRPO, implemented in 2015. The key benefit, so it's like essentially we're maximizing our policy gradient formulation we derived before, subject to the KL divergence, right? And I will not go too much into the details. We could do like talk a lot about this, but the key benefits from TRPO are that it provides a theoretical guarantee that each update will improve or not worsen the true performance of JPy. But kind of the downside here is that this KL constraint requires computing a Fisher information matrix, which is a matrix of second derivatives with respect to the KL divergence, of the KL divergence with respect to the policy parameters. And this is computationally very heavy. It's like n squared for the memory, and then n cubed for compute. And so there are like some approximations with conjugate gradients and so on. But in general, like it's kind of like very difficult to scale. Even like for deep networks, you need to even further approximations. So it's like not that popular nowadays, but still, you can see really compelling also like robotics applications, even here from ETH, how TRPO was used to train like quadruped locomotion, sim to real, and you can see very nice zero-shot generalization examples. And this is now a quadruped that can navigate challenging terrain, step over obstacles, and also like do locomotion over surfaces that it might not have seen during training. So like it actually works. All right, so TRPO has great guarantees, but we kind of like hate the computational cost. So the question is, can we get that stability without this expensive like second order math? And kind of the more popular algorithm, or that because it's a bit more easier to implement, is called proximal policy optimization, where the key idea is like, what if we can just clip the importance ratio instead of constraining it with the Kyle divergence? So kind of like this is how now our policy gradient update looks like. And essentially you can see like we are constraining this to be like inside some interval, and we are taking the minimum of these two clips. And because now this is like a simple first order method, like it scales linearly and works perfectly with standard optimizers like Adam, and this kind of like scalability is exactly why PPO is the backbone for many for training like large language models with like RLHF or like GRPO and so forth. The trade-off that we're making here is that we don't have a monotonic improvement guarantee anymore, and it's still near on policy. So we still need quite a bit of samples to learn PPO. So it's quite reliable and quite stable across many different domains and applications, but it's still mostly fundamentally near on policy method. In robotics, this is not playing. Yeah, in robotics, one famous application of PPO was done by OpenAI 2019, where they taught this kind of really dexterous shadow hand that has like 24 degrees of freedom to solve a Rubik's Cube. And this was again also like a sim to real kind of approach where they did a lot of domain randomization and simulation. But then, you can see it's like it can work across many perturbations, even like if it has like tight fingers. And yeah, maybe like one thing to note here is that so here PPO didn't receive like camera observations as input, like a state input, but essentially they had a more modular approach where they first had like a kind of perception network to extract like the position and orientation of the cube, which was then fed to PPO. All right. Okay, so here's the full objective of PPO. And you can see a lot of things that we have covered today come together in like this single formula. So there are like three terms, right? So first is the clipped surrogate objective we just derived for PPO. This is the actor loss that is updating our policy parameters, and it's trying to maximize the advantage while keeping the importance ratio in a safe range. The second term is the value function loss, and this is essentially a critic, and it's kind of being trained simultaneously to give us better estimates of the advantage function. Remember, like the advantage function requires the value of pi, right, of the states, and so the better our critic is, the lower the variance of our advantage estimates will be, and the more stable our policy. And the third term is the entropy bonus we discussed earlier, keeping the kind of policy from collapsing to a deterministic solution and maintaining exploration. And so here, like the key thing here is that this is now what we call an actor-critic formulation or architecture. And this is kind of very nice because now we are combining the best of both worlds of like policy gradients approaches to give us like, like direct optimization for the behavior we care about, as well as the value-based methods that we're using to give us low variance baseline through our critic. And so, as I said, like this gives rise to this family of algorithms called actor-critic methods, right? And the actor is the policy, and the critic is the value function. And they are, trained together. Maybe like one thing to note here is that the critic learns via TD updates, so meaning that it bootstraps from its own estimates at the next time step rather than waiting for the full trajectory return, which is a limitation that we had if we only used policy gradients for our actor. Right, we would have to wait until the end of the episode. And so this means that now this is quite much more sample efficient than using this Monte Carlo returns at the cost of a small bias that we are bootstrapping bias. And maybe for robotics, also interesting is that you can often train the critic by using privileged information. Because you don't use the critic at test time, so especially if you're using like a simulator environment or so, you can use like additional state information or privileged informations for your critic to reduce the variance, right? To get you like better advantage estimates. And then, like at test time, you throw the critic away, so it doesn't really matter. But it can help a lot your trading. Okay, I need to wrap up soon. So, so the last family of algorithms we will briefly touch upon today is the soft actor critic, right? Because this kind of like closes the loop, right? We have started like with very on-policy methods, and we've been trying to get more and more off policy to like be more sample efficient and use more previous data, right? And so soft actor critic is kind of the answer to that. It's a fully off-policy actor critic algorithm that trains the critic on a replay buffer, just like DQN in the lecture that we covered in the lecture before. So the actor has kind of these two terms, the exploration bonus that we saw before, and the exploitation which like just answers if I were to do this action today, like how many points would I get, right? And then like there is kind of this push and pull between these two, right? And then the critic loss is kind of a standard TD error. So the squared difference between what the critic currently thinks a past state action pair was worth and what it should think based on the actual reward received, plus the discounted value of the next state. And crucially also here, there is also this entropy term. That means that we want states that lead or we benefit, we push for states that lead to high rewards and also give you many different ways to achieve it, right? So this will get like pushed. And the key idea here is that the actor pulls all states from the replay buffer, but asks now the current policy and not the old one, what action it would take here today, right? So the critic acts kind of as a learned simulator, estimating how much reward the new action would have gotten in the old state, even though it never actually has seen this state-action combination. So that's really kind of the key here. There is one remaining problem. I will not go into too much details. This is pertaining to how to backpropagate through the sampling process, where you can use like a standard reparametrization trick for Gaussians, for example, also very used in variational inference and VAEs and so on. So yes, but I'm getting out of time. And there are also some real-world demonstrations of SAC on real robots from the original papers, both from Lego stacking, quadruped manipulation, or also dexterous hands. And yeah, to conclude, today we started with reinforce. It's kind of a very direct way to optimize a policy. We saw, it has some limitations, the vanilla version of reinforce, and we started to fix those by adding causality and baselines to kind of fight the high variance problem. And then we moved on to advantage functions to make our rewards relative to each other rather than absolute. Then we kind of hit the on-policy wall, because we are still kind of requiring to collect new fresh data for every gradient step. So we introduced importance sampling to allow us to take multiple gradient steps on a single batch of data. And we also explored adding entropy regularization to ensure the robot never stops exploring, and we still have like non-zero support for importance sampling. And then we also looked at different ways to constrain the change between the policies with the KL divergence and also with PPO, the simplified clipping, to kind of like bound how much the policy can drift in a single update. And finally, we reached soft Actor-critic, where we train critic fully off policy with a replay buffer similar to what we saw last lecture with DQN. And we see that this kind of achieves the highest sample efficiency from all our methods that we talked about today. And this is also why it's still today a very popular algorithm for also real robotics. Yes, with this, thank you for your attention.